So far in the module we have derived and discussed various characteristic times and lengths. For example, we have discussed minority carrier lifetime, dielectric relaxation time, momentum relaxation time, energy relaxation time, transit time, mean free time between collisions, and lengths such as de Broglie wavelength of an average thermal carrier, diffusion length, Debye length, okay, and so on. So now we need to discuss what are the utilities of these characteristic times and lengths. Now that is the topic of this lecture today. So we shall consider the following issues: qualitative explanation of device phenomena, how the characteristic times and lengths are useful for this purpose, then how they are useful in device simulation and characterization, and finally how they help us validate various approximations. Let us begin with qualitative explanation of device phenomena. Let us look at a p-n junction. Okay. Now suppose we are talking of operation of a p-n junction, right, and we want to explain what happens if you suddenly apply a forward bias. What are the sequence of events, how the conditions in the device evolve. So now in terms of our knowledge of various characteristic times, we could discuss or describe the evolution as follows. Moment you apply a forward bias, the p region injects holes into n region. Now once the holes are injected, there will be a space charge, and now this space charge will be neutralized in a dielectric relaxation time because of electrons which are drawn in from the contact. So we can say space charge neutralization. So before that we can start with hole injection from p plus to n. Now there will be electron injection also from n to p. We are not talking much about it because you know that the electron injection in a p plus region is really very small. So let us look at just one aspect, and we can also then extend this explanation to injection of electrons also from n to p. So the first stage is hole injection from p to n. The second stage is space charge neutralization, okay, by drawing in electrons. Now this happens in about 3 times the dielectric relaxation time of this region. Now thereafter, once you have excess electrons and holes, they will start recombining, and a steady state will be reached in about 3 lifetimes. So steady state, the third stage, is achievement of steady state in about 3 times the lifetime of holes in n-type semiconductor. Now once the steady state is reached, you will find that the excess electrons and holes, they decay over length, and you know that this length is about 3 times the diffusion length of holes. So beyond 3 times diffusion length of holes, you have no excess carriers, and these conditions here will be near equilibrium. So as a part of the steady state, you will have decay of excess carriers within say 3 times the diffusion length, okay. Now this is how you can describe the various things happening in a p-n junction, right, when you apply a forward bias. Now let us concentrate on the space charge region. Within the space charge region, if you plot the electron concentration, it would look something like this. From the edge of the space charge region, the electron concentration decays rapidly. Now what is the width of the space charge region? According to the problem that you have done in assignment, this depletion region, we are assuming that the depletion region on this side is really very small. If you want, you can include that also. So the space charge region width will be several debye lengths, right, of this lightly doped region, and within this, the extent in which this fall will occur, an assignment was given to you to find out how much distance does it take for the electron concentration to fall to 1/10 of its value, right. So it will fall to about 5% of its value, and this will also be of the order of debye lengths, except that this would be about 3 times debye length, whereas the XD would be a 7, 8, 9 times debye length, okay, about 7 to 9. Now from here you can figure out that the depletion approximation will be valid for the depletion region if this distance is small compared to this distance, okay. In other words, if your depletion width itself turns out to be about 3 times debye length or smaller, then your depletion approximation will not be valid. So this is how you can describe the various conditions in a device based on the characteristic times and lengths. Now we have considered the example of a PN junction. Next, let us take up a MOS junction or a capacitor. Now this is a MOS junction. Let us say we apply a step voltage to this. We suddenly apply a step voltage, a forward voltage in this case, or positive voltage, so that I want to create an inversion layer on this side. I am applying a gate voltage that is more than the threshold voltage. Now how will the conditions in this device evolve to create the inversion layer? Now what will happen is, the first stage would be creation of a depletion layer, right, because the majority carriers holes can be quickly removed from here in dielectric relaxation time. So creation of a space charge in dielectric relaxation time from majority carriers. So let us say this is the depletion region edge, and this is the space charge that you have created because you applied a forward voltage. It immediately needs a charge to the field that you have created needs a charge here to terminate. Now this XD will be more than the depletion width under inversion, okay, under steady state conditions when inversion happens, because there is no inversion layer here. The entire electric field has to terminate on depletion charge. So this will happen in about 3 times the dielectric relaxation time. So creation of XD greater than XD max, okay, because your gate voltage is more than Vt, in about 3 times dielectric relaxation time. Now once this has happened, you have created a depletion layer like this. Now inside this, the PN product will become less than Ni square, and electrons and hole pairs will be generated. Similarly, electron and hole pairs generated here, part of those, some electrons will get attracted to the surface because the field is in this direction, it tends to attract electrons. So progressively what will happen is that electrons generated here within a diffusion length from the depletion edge and electrons generated within the depletion layer, okay, they will all start migrating towards the interface to create the inversion layer. And as the inversion layer is built up, the depletion layer will progressively collapse, reduce, and ultimately reach the XD max, which corresponds to the steady state value, and at that point inversion layer will be formed. So the second stage is formation of inversion layer. And how much time will it take? Well, we can write a simple formula as follows. You know that under steady state the inversion layer charge would be Cox into Vg minus Vt, where Vg is the value here, this value is capital Vg. Now that is the inversion charge. To create this charge based on the charge is created from generation. So now you know the formula for generation time is Ni by tau g. This is generation rate from our SRH theory we know. So using the generation time constant here, okay, this is equivalent to the lifetime. Now this is generation rate, and generation will happen in the depletion layer as well as within a distance from the depletion layer. So let us say this is minority diffusion length Ln. Now note that this boundary is progressively shifting, right. So the Ln, so this boundary also will keep shifting. So always within a diffusion length from the depletion edge at any instant. So we can write here xd plus Ln. Within this region the generation will happen, and all these carriers will accumulate here and create the inversion layer. So formation of the inversion layer happens in about this much time. Now let us check whether our dimensions are correct. You see that in denominator I have not put q because numerator contains the charge, so I have to put a q here. So Ni is per centimeter cube, this is length, so this is per centimeter square. Numerator also is per centimeter square because Cox is normally in per centimeter square. So this is about the time. So this is how we can describe the formation of inversion layer when you suddenly apply a step voltage at the gate equal to a value more than the threshold voltage. So first depletion layer is created in dielectric relaxation time 3 times the tau d, and then within the depletion layer and within a region equal to about diffusion length from the depletion layer, electrons are being generated, and those electrons are migrating towards the interface because there is a field, they are attracted to the interface and they form the inversion layer. What happens to the holes? Well, the holes move out. So this process can be shown like this. The holes are moving out and the electrons are migrating towards the surface. Now one more example that we can describe in terms of the characteristic lengths is capacitance of the MOS. Suppose this is your MOS capacitor or junction. What is the flat band capacitance if you want to know? So we have applied a voltage equal to the flat band voltage here. Under flat band conditions, you know that under DC flat band conditions there is no charge here in the semiconductor. Now when you want to find out the capacitance, it is a response to small signal voltage, that is why small signal voltage has been shown here. So in response to this voltage, a space charge layer, a modulating space charge layer will be created. Now what would be the extent of the space charge region here? Now that extent would be about a Debye length, because we know that in our discussion of Debye length that the space charge regions, they exist within about 3 times Debye length. So here the region width will be of the order of Debye length, and therefore the semiconductor portion will have a capacitance given by epsilon s by Ld. So note that this capacitance is not infinity. So if you write the flat band capacitance formula, it will be parallel combination of oxide capacitance, a series combination of oxide capacitance and this semiconductor capacitance. So it is Cox and Cs in series, and that is why at flat band the capacitance is less than Cox, okay, because you have this capacitance which is non-infinite because the Ld is not 0. Let us take one more example, the example of a MOSFET. Here we want to bring out the utility of transit time. Suppose I have a MOSFET like this, I have applied a drain voltage and I have applied a gate voltage which is suddenly switched from below threshold to above threshold. So from 0 it is switched to a voltage more than threshold voltage. Now when will you feel the drain current? So far we had not applied a drain source voltage. In this case, for example, even here the voltage was switched from 0. We talked about formation of inversion layer and so on, but there was no drain and source contacts. So we are moving to a slightly more complicated situation where we have now put the drain and source contacts. So now the issue is not just formation of inversion layer everywhere in when you have a gate to bulk voltage. So you have a drain voltage and you want to feel the current at the drain end. When will this happen? So here you can bring in the concept of transit time. You know that the electrons at the source end will take about a transit time to reach the drain end, and therefore for this formation of the full inversion layer from source to drain, it will take about a transit time. So moment you apply a gate voltage, the inversion layer will start building up. So electrons in the inversion layer will take about a transit time to reach this drain end, and therefore you will find that the IDT in response to VGT will appear after a transit time. So the IDT versus T would look something like this, where this duration is about the transit time of carriers from source to drain. Let us see how our characteristic times and lengths can be useful in device simulation. Consider the problem of simulating a surface recombination using volume recombination. So let us say we have a simulator which does not give provision for specifying surface recombination at a particular surface, but you know that you want to simulate a device in which there is surface recombination, right? In practice there is surface recombination. So how will you use the volume recombination provision of the simulator to realize a surface recombination? That is what we are discussing here. Now let us say this is an n-type region and you want to simulate a surface recombination velocity s at this left surface. Let us say the lifetime of this bulk region is tau suffix p. Now this is the region of the device. We have not shown the other device here because that does not concern us, but please remember in a simulation situation may be more complex and you will have other regions connected to this region to form a device. Now how do we simulate a surface recombination at S? Now let us see what is the effect of surface recombination. The effect of surface recombination is electrons and holes will be moving towards the surface and recombining over there, the electron hole pairs. To simulate this situation we need to actually simulate a carrier concentration variation shown here. We have shown the excess hole concentration as a function of x. You can similarly show excess electron concentration. You know that quasi neutrality holds usually and therefore delta n will be equal to delta p, at least approximately. So we would like to simulate a minority carrier distribution as shown here. The value of this excess hole distribution is delta p infinity for x very large, and it dips down to delta p suffix 0 at x is equal to 0 where you have surface recombination to create this tendency for the hole current. Now you know that this variation will occur over a distance equal to about 3 times the diffusion length of holes. So we really want to simulate electron or a hole current towards the surface perpendicular to the surface given by this formula. So the magnitude of the current divided by q is surface recombination velocity s into the excess hole concentration at x is equal to 0, that is this value. Now you can do so using a semiconductor region. So what we are doing here is we are extending the semiconductor bulk here by another semiconductor region, right? This semiconductor region is such that the lifetime of holes in this region is very small compared to the lifetime of holes in the bulk here. Now because the lifetime here is smaller, there will be a tendency for electrons and holes to move into this region and recombine over there. So please note that similar arrows exist in the bulk of the parent n-type region also. We are not showing those arrows because we are showing only the difference in the recombination between this extension and the parent region, semiconductor region. Now how much should this recombination be? This is what we have to see. So this recombination should be so as to simulate the surface recombination velocity. Let us assume the width of that region is W. To start with, let us say this W is more than 3 times the diffusion length of holes in the region W, that is L suffix W. Now L suffix W will be much shorter than L suffix P, that is this, because lifetime of holes in this region extension is much less than the lifetime tau P in the bulk. Now what will be the effect of this on the excess carry distribution? So the excess carry distribution will decay to 0 as shown here in this region. So far away your excess carry concentration will decay to 0. Now you might like to think, now why is there excess carry concentration here at all? Now that really does not concern us at this point. There could be many reasons for excess carriers being present there, because it is a device. There may be injection from some other region, or there may be light being shown on the sample and therefore there is volume generation. That does not concern us, right? What we have to concern with is the effect of that. So whatever is the source of excess carriers here, please note that source of excess carriers is not there here, okay? This is simply a semiconductor extension. So here far away from this surface your excess carrier concentration will go to 0. Now we want to adjust our W and tau W in such a way that the value of the hole concentration, excess hole concentration at the surface remains equal to delta P naught. Now if you do that, then we would have simulated the surface recombination velocity S according to this formula. Now let us say we choose a W much less than the diffusion length of holes there. This is to simplify matters. Now what would happen is this hole distribution now would remain almost approximately constant over this region, okay. From our knowledge of the characteristic length, we know that if the width of any region is much less than the diffusion length there, the excess carrier concentration would remain approximately constant, the decay will be very small. So that is why the hole concentration is now assumed to be approximately constant over W. Now this will help us simplify the formulation of the problem. So now we can write that the current divided by Q, that is the flux, is equal to W, that is the width of this region, into delta P naught divided by tau W. Now this is actually the recombination shown by these arrows here. So the flux that is represented by these electron and hole arrows perpendicular to the surface here is the same as the recombination taking place here, taking into account the dimensions properly. So here whenever we talk about the flux, we talk about per unit area. Therefore this is the volume recombination per unit area of this surface. So if you want to take into account the actual area, then this formula would be W into the area into delta P naught by tau W. However, then you will have to change the formula for the flux and you will have to put an area here also. Now equating these two, what do we get? So we get the surface recombination velocity as W by tau W, because delta P naught will cancel. Now this tells you that if I choose an extension W which is much less than LW, then by adjusting my lifetime according to this formula I can simulate the surface recombination. So this is what is summarized here. S is approximately equal to W by tau W, and W is much less than LW. These are the conditions. So these imply the width of your region that simulates surface recombination should be much less than dP by S. So I can combine these results, okay, because this formula is valid only under this condition. So I leave it as an assignment to you. You substitute in LW square root of the dP into tau W, because that is what the diffusion length is, and then combine these results and you will get this formula. And similarly the condition on tau w would be it should be much less than dp by s square. So this again can be obtained by combining the results here. Okay. Now you must take care that tau w remains much less than tau p also. So that is the additional requirement. The summary of our discussion is that a surface recombination S can be simulated using a semiconductor extension of width w satisfying the conditions that we have just now outlined, and a lifetime tau w also satisfying the conditions we have outlined. The important thing about tau w being it is much less than tau p. So w and tau w simulate S is equal to w by tau w so long as w is much less than dp by s and tau w is much less than minimum of dp by s square and tau p. Now let us look at device characterization. Where can our ideas of characteristic length and time be useful? Let us discuss determination of doping profile from CV measurement. Now how do you measure the doping profile from CV measurement? Consider a p-n junction or a Schottky junction or a MOS, right, capacitor. So what you do is you measure its CV characteristics, right, and you know that the capacitance voltage characteristics will tell you the doping profile. So for example if you take this MOS capacitor, as you change this voltage your depletion region changes, right, and that is how you can find out what is the doping at the edge of the depletion region. There is a formula, you must have studied this formula in the first level course. Now we are talking about that CV measurement, right, to measure the doping profile. So what is the doping variation in the X region in this bulk, or for example if you take the p-n junction, what is the doping in the lightly doped region, what is the profile here. Now CV measurements are sensitive to mobile majority carrier concentration rather than doping. Although you are measuring doping, you are actually you want to measure doping, what the CV measurement does is monitors the mobile carrier concentration, mobile majority carrier concentration, and now you know that you cannot always assume the majority carrier concentration is approximately equal to doping concentration. Why? Because if the doping varies too rapidly there can be space charge regions. So that is the point that we are bringing out here. What should be the variation of the doping so that you can capture the variation. So for a small abrupt change in doping the mobile carrier concentration varies over a few LD. Now this is the picture. So if you take an n plus n junction changing where doping changes abruptly at this surface. Now this is the abrupt change in doping. Evidently the mobile carrier concentration cannot change abruptly because it will result in infinite diffusion currents at the point where abrupt change is occurring, and it will change gradually. And now from our knowledge of the Debye length we can easily anticipate that the space charge region over here will extend to about 3 times the Debye length, right, and similarly on this side also it would be 3 times the Debye length, where Debye length corresponds to the Debye length of this region over here, which is slightly smaller because doping is higher. So this is what we mean by saying the mobile carrier concentration varies over a few LD. So now since you are monitoring this mobile carrier concentration in CV measurement, in effect you cannot capture this rapid variation in doping, right. So this is what is the limitation of the CV method. So it says that abrupt changes in doping occurring in a scale less than LD cannot be resolved in measurements. Okay. So if you have a doping profile, let us say which changes abruptly like this step like profile, you cannot get the steps out from a CV measurement data. So you will get a more smooth variation. So what the characteristic length Debye length tells you is that the doping variation should not be very rapid over a scale of LD. So that it gives you some idea of what kind of doping variations can be captured. Let us come to validation of approximations. A large number of approximations are used in device analysis and modeling: quasi neutrality, quasi-static approximation, neglect of generation recombination. Some of these we have discussed already. Then we use the carrier temperature formula. This carrier temperature formula, if you recall, we had derived using steady state and uniform conditions in the semiconductor, but still the formula is used for even non-uniform and high frequency conditions. So that is the approximation that we are talking about, right. So how is it valid? Then we are using the various forms of transport equations, drift diffusion transport equations, and balance equations, Boltzmann transport equation, and so on. So each of them has their validity range. Then we are making a particle approximation, and finally we use an energy band model. So all these things are often used in device analysis. So let us see how the idea of characteristic times and lengths enables us to validate these approximations. Let us take quasi neutrality. This approximation holds in a semiconductor region which has a high mobile carrier concentration, whose doping does not vary significantly over LD, because as we discussed just now, if the doping varies rapidly over length scale LD, then there will be a space charge region, because the mobile carrier concentration cannot vary as rapidly. So then quasi neutrality, the neutrality will be violated, because in this region you have space charge and here also you have space charge. Now a region which is several LD away from fixed charges tends to be quasi neutral. You can see here, for example, a region which is in this place, that is beyond 3 times LD from the source of the space charge, will be quasi neutral, and similarly on this side, right. So that is what is meant here, a region which is several LD away from fixed charges. Now in this case there is no specific location of fixed charge, but if there is a source of charge and if you are away by several LD from there, you will have quasi neutral region. So the quasi neutrality will be valid for all these cases. Now look at the high mobile carrier concentration. Why this allows us to use quasi neutrality? This can be understood in terms of the time constants, dielectric relaxation time, and the Debye length LD. Now high mobile carrier concentration means small tau d and small LD. You know this from the formula for these characteristic parameters. So small tau d means operating frequency tends to be much less than 2 pi tau d reciprocal of this quantity, right, because if tau d is small, this quantity would be large, and therefore your operating frequency would be much less than this, and that means the carrier concentration does not change much over a duration tau d. Now small LD means fixed charges tend to be screened within a short distance, leaving most of the region quasi neutral, because we have just now seen that if you are several LD away from fixed charge, you are in a quasi neutral region, and if LD is small, this amount by which you need to be away is really very small, so most of the region would be quasi neutral. Let us look at quasi static approximations. Let us look at these two approximations. Now this is a quasi static approximation of the carrier balance equation. This is a carrier balance equation. You can neglect dou n by dou t so long as your frequency is much less than reciprocal of 2 pi into minority carrier lifetime, that is this time. So in other words, we are saying that this term will be negligible compared to this term so long as your frequency follows this. Now this is how you get a condition in terms of your characteristic time for validity of this approximation. Similarly, if you integrate this equation, you get an equation of this type. This is called an equation for stored charges. Now this kind of an equation is useful, for example, in a MOSFET. So here let me explain what this equation is. This term is the source current into the source terminal. This term is the bulk current, and this term is actually the drain current under steady state conditions. So we have used the transit time concept to write the current. You know that under steady state conditions the transit time from one end to the other end can be written as ratio of charge by current, and so the current can be written as the charge, that is inversion charge, that is causing the current divided by transit time. This is under steady state. However, we are writing the formula under transient conditions. So there is a negative sign here because for electrons the inversion charge is negative, right, and therefore there is a negative sign here. Let us spend a few minutes to explain how you get this equation from this equation. In fact, let me first point out the one-to-one correspondence. This term is obtained by integrating this term on the left hand side. These two terms emerge from integration of this equation, this term, the divergence of the current density. When you integrate this, you get these two terms for the two limits of integration, the drain and the source. There is really no excess generation in the MOSFET. We are assuming such a condition because of light or impact ionization and so on. All these generations are neglected, so this term is not there, and this bulk current is actually a consequence of the generation recombination current that is coming by integration of this term here. Okay. Now let me quickly show you the steps in which the terms emerge. Now let us look at the MOSFET here. The N is the electron concentration here that is causing the inversion layer, right. So now how do I write a formula for the inversion charge? You know that Qi, the inversion charge, can be written as integral of the electron concentration over dy with respect to dy, that is y. So in this case we will assume that this direction is y and this direction is x. So integrate along this direction. Then you should also integrate along this direction, right, because you want the total charge. So dou x, and you should multiply by minus q. Then you must also take into account the fact that there is a width direction here, w, okay. So in this direction, that is w. So we have to multiply this whole thing by w. So w into dou y into dou x. So you integrate in this direction, integrate in this direction, and take into account the fact that there is a w in the direction perpendicular to the board. So you get a volume w dou y dou x. Multiply the volume by the charge concentration, you get the number multiplied by charge, which is minus q because it is electrons. So that is really your Qi. Now let us look at the currents Id and Is. So Is is the current here in the source. Now current anywhere, you want to get the current. How do you get the current? From Jn, well, your current In at any x is equal to integral Jn dou y into w, okay. So you are integrating over y and you are taking w, that is a width in that direction. So w into dou y is nothing but the area of cross section of the current flow, right. The current is flowing like this, it has an area of cross section. If I show it in 2 dimensions, it would be probably like this. Your w is in this way. So something like this, your current flow is in this direction, this is dou y and that is w, okay. So this is the area, w into dou y, that is J. Now what about the bulk current? The bulk current is the current here, that is Ib. Now this is because there is a generation of electron hole pairs. The electrons move to the positive drain contact in a n-type MOSFET and the holes move out here. So that generation is represented by this. So I can write IB as, so let me write this as small in, because the reason is that things are changing with time. So IB is n minus n naught by tau. Again, as we have done here, we need to integrate over dou y dou x and multiply by minus q to get the charge over here and w. Then it gives you the current IB. Now note here that this was charge, but this is current because there is a time constant in the denominator here. You compare these two, the numerator gives you the charge and this is a time constant, that is IB. So now how can I get a relation between these from here? So if you integrate now, so what I do is I multiply this by dou x dou y, right? I multiply this also by dou x dou y. Now this is dou by dou x, so the dou by dou x, in that dou x has been brought here, and I multiply this by dou x dou y. Then I multiply by minus q, because I have to get minus q here. If I multiply by minus q, this q goes away, you get a minus sign, and multiply by minus q here. Then I multiply by w, I have to get w here. So that gives you a w here, and it gives you a w, this w that you require here. Okay, let me put it on this side because there is no place here. So now what I do is I integrate. So when I integrate this, I am integrating, when I am integrating with respect to y, it is a double integration. I integrate from y equal to 0 to y equal to infinity, and when I integrate in x direction, I integrate from x is equal to 0 to x is equal to L. This is the channel length L. Okay. So you have to do the same thing on each of these terms. Okay. Now what will the result be? So this will give you now the dou by dou t, because this time derivative can be brought out when you are integrating with respect to x and y. So I will put it like this, I will remove this out. So this term will reduce to dou qi by dou t. Let us go to the right hand side. This term will reduce to, you have seen here, so here you are going from y equal to 0 to infinity, and there is a dou of Jn. So when I move this dou out here, when I am sorry, this has to be so I can integrate from y equal to 0 to infinity, and before, when I integrate with respect to x, I take the dou out here. So x is equal to 0 to x is equal to L. So this quantity really will turn out to be, according to this result, the value of In at x is equal to L minus value of In at x is equal to 0. Okay, but there is a negative sign here, and therefore it will become minus of INL plus of IN0. Now what is INL? So electron current at L, this is nothing but the drain current. The drain current is inward and the electron current is outward, right? And therefore this quantity can be written as minus of In is ID, minus of In at L is ID. And similarly this quantity can be identified as minus of Is, that is the source current, this again downward, whereas your x is upward. Now what about this here? So this current can be directly related to IB, there is a minus sign, so you have minus of IB. So minus of IB. Now under steady state conditions this ID is written as minus of Qi by transit time. So we use the steady state result in this transient case to solve this equation in a simple manner. So this kind of an approximation you can do if your dou Qi by dou T is small, that is a so called quasi static approximation in the context of MOSFETs, the very important approximation. So you can see from here that this approximation can be done if this term turns out to be much less than the magnitude of Qi by transit time. Okay. So that is what is shown here. So dou Qi by dou T, this will turn out to be much less than this quantity, and the quasi-static approximation will hold if your frequency is much less than 1 by 2 pi transit time. Let us look at some other quasi-static approximations. So you take Maxwell's equations, curl B is equal to mu times J, that is mu times Jn plus Jp, plus the J also includes the displacement current. Now often we like to neglect the displacement current because we say the frequency is not very high. Now what is the condition for that? So you can write this sum in this form, where we have assumed a drift current for Jn and Jp. So it is expressed in terms of E, and from here it is very clear that I can assume dou by dou T of E as negligible if it is small compared to E by tau d, and therefore in terms of the frequency this condition will be valid if f is much less than 1 by 2 pi tau d. So this is how a knowledge of the dielectric relaxation time helps us to explain the conditions that should be satisfied, the frequency that should be frequency conditions that should remain in the device for the quasi-static approximation to hold. Similarly curl E is minus dou B by dou T. In this case we can neglect the time varying magnetic field when the device size L is much less than the electromagnetic wavelength. We will not spend much time in explaining this point. You know that if the device size is small then it does not radiate, right. If you want an antenna then the antenna length should be comparable to the wavelength of the frequency that you want to radiate out. This you might know from your basic knowledge of electromagnetic fields. Something like that is being used here. So such a radiation will not happen, we do not have to bother about any radiation, or in other words we do not have to bother about time varying magnetic fields if your device size is less than electromagnetic wave length. And when you convert this into frequency, so writing the electromagnetic wavelength in terms of the velocity of the wave and the frequency, you get this inequality. So frequency should be much less than the device length multiplied by square root of mu epsilon, where mu is the permittivity, mu is the permeability and epsilon is the permittivity. Then we have come across the quasi-static approximations of energy balance equation and momentum balance equation. This is what is shown here. So just repeating those facts, dou by dou T of Wn can be neglected if your frequency is much less than 1 by 2 pi energy relaxation time, and dou by dou T of Jn can be neglected if your frequency is less than much less than 2 pi momentum relaxation time reciprocal. We have used this formula for carrier temperature derivation. Finally the Boltzmann transport equation, we can neglect the time varying term on the left hand side if your frequency is much less than 2 pi tau c, 1 by 2 pi tau c, where this is mean free time between collisions. Now a caution here, we are using the f symbol in two cases. So here this f is not the frequency, as you would have already recognized. This f here in the Boltzmann transport equation is the distribution function, whereas this f here is the frequency. Okay. before closing this lecture let us look at one more approximation that is commonly very useful, neglect of generation recombination. Critical regions of modern VLSI devices are much less than the diffusion length of minority carriers in the regions. So critical it is the length of the critical region, that is what we mean here. Now because this is a fact, we can say that generation recombination plays little role in VLSI device operation and can be neglected in the continuity equations. So this means your continuity equations for VLSI devices could look something like this, where both G and n minus n naught by tau minority have been neglected. So that is a great simplification. In addition, if steady state conditions prevail, then the continuity equations in such regions is simply divergence of J n or P is equal to 0, right. That is really very simple. Now with that we have come to the end of the lecture. So in this lecture we have discussed with many examples the utility of the knowledge of characteristic times and lengths. We will consider some more examples in the next lecture and also summarize this module.